Alright, so we are now talking about the wind in more detail so that we can understand why is it that the wind even blows in the first place. Alright, and if Mr. Ryan's getting a little loopy, that's true because I am not full of energy anymore. Alright, so here we go. How can we measure the wind? Wind is a result of uneven heating on Earth's surface. So if you've got a place that's heating more than another place that might be on the cooler side, you're going to be causing air to move, and it might rise in one place, sink in another, and it's all got to fill in. Oh my gosh. Do you remember what that's called? I think I do. It's called convection. We have been talking about convection for months. So in this case, this uneven heating, convection cells cause wind. I hope you've annotated. At least at some point you've been reading through, you've been annotating. I know that we skipped through it pretty quick, but I would expect you to still be doing some of this reading first so that this video is not just brand new to you, okay? Depends on your learning style, but you'll get more out of this if you're doing some of the reading first. Alright, so this causes there to be a difference of higher and lower pressures, and because of that, all energy flows from high to low. We've got the same issue. We've got winds. All of it's coming from high pressures to low pressures. That's where it's flowing in through, okay? Now, we have isobars that we can connect. Ooh, we're back to the mapping unit where we might be connecting points of equal pressure in this case. So now we're getting back to this isobar bit, where each of these dots is 1,002 millibars. Each of these dots is 1,000. All right, so we're going to have to recall those particular skills. All right, now, what I'd like to point out, though, is just like the steepest side of a hill, the steepest pressure gradient is where the lines are closest together. A steep pressure gradient also results in your fastest winds. So if we were to compare all the areas, A, B, C, D, and E, the location that is where all the lines are closest together would be D. So your fastest wind speeds are right here, smack dab around the border of Nassau and Suffolk County, which is really hard to tell, but that is the island, and this is the city. The city. All right, so let's keep moving. Now we have winds that also form at the beach. You have sea breezes, and you also have land breezes. Most of us are only interested in the sea breeze because let's face it, it's a hot day. We want to go to Coney Island, Brighton Beach. We want to go maybe to Jones Beach. Maybe if you happen to go all the way over to Jersey, you might go to the beach there too. But you want that nice cool breeze coming off that ocean so you can just sit there and cool yourself off. All right, so how does it work? Well, during the day, land heats up faster. And you might ask yourself, Mr. Ryan, why? But you should already know. Because the land heats up faster because it has a lower specific heat. Remember that sand? Way back in specific heat. If you want to rewatch it, oh, the beauty of videotaping myself. You can go all the way back and you can watch what I did, and then watch this right now. You can have even two windows open. You can have me talking twice. Oh my God, you can't be talking here about specific heat, and then you can flip to this tab and you can see me talking about wind. Oh my, I might do that at home just to see what that's like. I'm probably going mind blown. All right, so sands. They have a high specific heat, so they heat up faster. This liquid water has the sand has a low specific heat, so it heats up faster. The liquid water has a high specific heat, so it heats up slower. So this stays relatively cool during the day. This warms up very fast. Warms up, so the air warms up and it travels up. And over here, where the water stays cool, it cools down the air, so the air starts to sink. And then you've got to fill this thing in, and you've got a convection cell. All right, so at nighttime, the opposite happens. if the sands heat up fast, they will cool down faster because they don't retain that heat as well. And the water ends up retaining the heat, so it ends up causing the air above it to warm up at night. So it goes up here, but over the land it cools down and it blows out to the ocean instead of the sea breeze where that air is blowing in from the water. Right? Now, let's get a little bit more detail here about maybe measuring winds and planetary winds and how the wind blows around a high pressure and a low pressure as we continue to march towards understanding weather maps. All right, so wind speed and direction. We got two devices. One of them is called an anemometer. Okay, the anemometer measures the wind speed. So it's like blowing on that fan like a pinwheel, except that pinwheel is hooked up to a probe, and that probe is going to measure the speed. Now, in wind vane, you got this little rooster. I was just about the cock-a-doodle-doo. I don't think it's right. So anyways, here you have your rooster on top of your wind vane. As the wind blows across this fin, the fin will point the arrow in the direction the wind is coming from. Okay? So an example, if here is my wind vane, and all of a sudden the wind hits here, it's going to turn the pointer towards the direction it went. If the wind hits here, it's going to turn the arrow and point in the direction it came from. So a wind vane points in the direction the wind came from, which is part of the reason why we name them for where they came from. All right, let's go on a little bit further. You should have done a little bit of reading here. Now, if everything were perfect and the wind were blowing and we had these convection cells, we would expect that the equator, the hottest place roughly on average on the planet, is going to be the place where all the air on the planet rises and then it hits the top of the tropopause, or hits the tropopause, top of the troposphere, spreads out, moves to the poles where it's the coldest, and sinks. It makes one big giant convection cell. That would be so easy, except nothing's ever easy. So one thing that the Earth is doing, it's rotating. So because the Earth is rotating, this causes the winds to deflect. What I will do is I will upload a video for you to see how the Coriolis effect works. Okay? But for now, as I'm talking about it, I want you to just pay attention to what I'm saying and maybe some of the actions I'm taking, or maybe my analogies will help as well. So we've got the Earth is rotating. So because it's rotating, these winds will deflect, or we could say that they bend due to the Coriolis effect. In the northern hemisphere, everything deflects to the right. Okay? In the southern hemisphere, everything directs to the left. Let me pause and get something for us. All right, so we've got our globe, good old Earth. Earth, remember, with a PH. So, if we're thinking about the northern hemisphere, right, this half of the globe, the Earth is rotating from east to west. So, what we have to make sure that we understand is that when the Earth is rotating, it's going to cause anything in the air to deflect in a different direction. So if, maybe I can zoom in a little bit here. So if I am starting in New York and I want to fly to Florida, I can't do it straight, because once I take off and I try to fly to Florida, the Earth is going to be rotating underneath me. So I'm going to end up maybe in Atlanta, Georgia, or I might end up in something like New Orleans, if I go down far enough. So if I were to turn this around for us to see, again, if I am in New York and I'm trying to fly straight down to Florida, the Earth is rotating underneath me. So really my pattern has gone off to the right instead of going straight to it. So that's why planes, if you're flying to Florida, tend to fly a little bit out over the ocean so that when it rotates the Earth, or when the Earth rotates, you end up at your destination. So in the northern hemisphere, that is Coriolis affecting your ability to end up at your destination if planes don't set a course slightly off so that the Earth is rotating underneath it as it's going there. All right. So I think that hopefully is a decent example for now. I will try to upload a video or link a video to another YouTube video for you to see that maybe in a simulation. All right, now because of Coriolis, it causes us to have multiple bands of areas within Earth or on Earth's surface which deflect due to that. So when we get further into climate, I'll talk more about all of these and what impacts they have due to latitude. But for now, notice that all winds go out into its right in the northern hemisphere. So everything above here on page 14, out and to its right. This is out and to its right. So the top arrow, it's going out and to its right. This bottom arrow here is going out and to its right. Down in the southern hemisphere, it's going out and to the other way. I don't want to say the direction. I don't want to get you all messed up because I want to make sure you remember the northern hemisphere. It's going out and to its right. Out and to its right. It's right. So if you say anything else, you're wrong. It goes out and to its right because it's right. That also causes these other little convection cells to form because of what's occurring here due to the uneven heating and tilt of Earth and the rotation that's taking place. All right, let's go to the next step. So because of Coriolis, because of the deflection of winds, we end up with a situation where in high pressure, so add an H, add an L, I'm going to add an L in red because low pressures tend to be warm. So high pressure, think about it. If you're putting pressure on something, you're pushing down on it. So high pressure air is sinking air. Sinking air means that it's cooler and more dense. So in high pressure, we tend to have slightly cooler air and it's pushing down, okay? It's pushing down on that air. For low pressure, it's rising. It's generally warmer, and it tends to be a little less dense because of that heating. And it rises up. All right, so what's important now, though, is explaining that in a high pressure, that air, and let's see if I can do a little quick analogy of this, a quick imagery. Okay. Let's do this with materials here. I have pretty much ready to go. As always, you know Mr. Red loves to rip up paper. Ooh, am I gonna get it? Ah, there we go. I'm gonna make such a mess like I always do. You kids, you don't even know. All right, so let's get something to have a little fun with, shall we? We shall, we shall, we shall, we shall. All right, let's zoom in on this. There we go. All right, so here, let's pretend all of these little pieces of paper that I've ripped up, they are all little air parcels. tiny little air parcels. And so let's talk about what happens when this when this whiteboard ends up becoming the air that's either sinking or rising up. So if I'm going to drop this down, think about for a moment, stop and think. What do you expect to happen to the air underneath this? And what do you expect, maybe hypothesize, what's going to happen to all of these little pieces of paper that are just sitting here? So think about that for a moment, pause, maybe stop and jot into your notes what you expect, and then let's do this. And in true Ryan style, let's make it epic. Woo! That was a good one. How'd you like that? So, where did it all go? It went out. And because it went out, it was because of the displacement of the sinking air underneath this whiteboard that caused the air to move out. I put more pressure down, just like that sinking air, and that air caused wind in all directions outwards. Now, if we were on the planetary size scale, we would expect it to go out and to the right, but because we're not traveling over hundreds of miles, we're not going to see that curvature due to Coriolis. Okay? Now, opposite, let's do it the other way. So let's tear up some more paper, because you know I love to do that. Don't worry, I'll recycle it all. I'll recycle it all. Maybe at home. We'll see. All right, so let's do this. All right, let's get all this up. I don't know about you, but I'm having fun. You know me. If you can't entertain yourself, life is just awfully boring. So find ways to entertain yourselves after you get done with this video and after you do this practice. You know, take a deep breath. Hopefully today is a nice sunny day, and hopefully things are starting to let up and we're getting better, newer, and nicer information from everything. All right, now, hopefully I don't throw my back out on this one. Now, instead, we go the opposite. We were just doing the high pressure up here. So we ended up with, wow, look, I got paper all over here. We were just doing high pressure, so all the winds go out and to their right from a high pressure. Okay. Because of that, it causes there to be an overall clockwise rotation. So high pressure systems tend to rotate clockwise. So for low pressure system, the air is going up. So take a moment to think about, what do you expect to happen with this when I lift the whiteboard up? Hypothesize what will happen to the air, what should happen to these pieces of paper, and then we'll come back to discuss how that's represented here in this image. So pause the video, stop and jot something down over here, and let's do this. So 3, 2, 1. Not as impressive as I thought. Let's do that one more time. Ready? All right, well, you get the idea that when I was moving this air up, you needed air to filter in so that it would start to refill, and that refilling process of air caused our air particles to start moving up with the board. So a low pressure system's warm air rises up and away, and so we would have air coming in and bending to its right. In and bending to its right. In and bending to its right. All the way around. If you look at the direction the arrows are going, they sort of look like they're starting to turn counterclockwise. And overall, a low pressure system will indeed rotate counterclockwise. All right, I want to share with you one other thing called the right hand rule. I don't know where we're at for time. We're close. We're doing pretty good today. All right, so let's see. One other way for us to remember how to do the right hand rule. Which side's cleaner? We'll do this side. All right. I just about knocked the wind out of myself. All right, here we go. So, if you take your hand and you create kind of like a claw with your straight-fingered claw, what you can represent is that these fingers, will represent the wind. This aspect, the back of my hand and my palm, will represent the air that is high up in the atmosphere, sinking for high pressure. And as that air sinks, my fingers start pushing outwards, just like the wind was pushing outwards in all directions here. And turning it to its right will cause your whole hand to rotate clockwise. The opposite is true. So let's do that one more time before we go to the opposite. So this cold, more dense air sinks, pushing down. The fingers represent the air that's blowing out and away from that high pressure. And due to Coriolis, everything goes out into its right, so it's all turning clockwise. So for a low pressure, we have warmer air that's resulting in less dense air, which is rising. Because it's rising, the air has to fill in underneath it. And we know that it goes in into its right. So as they come in, my index finger, you'll see from this video, is going in and then to its right. Its right. Right here, it's turning in and to its right, causing our whole low pressure to turn counterclockwise. So again, a low pressure, air is less dense, warm, it rises. That wind underneath is filling in and going in to its right, causing it to turn counterclockwise. Okay? Now, let's get to some practice questions and eventually we'll be through with this topic. All right, so here, pressure systems guided and independent practice 1. I'd like you to try these 2 questions here and then pause the video, give it a shot. If you need my access points, you'll find my access points here for pressure systems access points in case, there we go, in case you need them. Okay? All right, now that you've had an opportunity to pause the video, I hope you've given this your best shot, read through the question, maybe annotated if you needed to on the diagrams or in the question or answer. So question 1, in which cross-section, cross-section, cutaway view. Cross-section is a cutaway view, all right? Which cross-section do the arrows represent the most probable direction of air movement over land and water surfaces at an ocean coast on a hot, sunny summer day? So it's daytime, you've got beach and ocean. We have to start thinking about which side heats up first and which place will cause air to rise up faster and away. So this one, this is showing that this interface is where it's heating up and the air is rising. I don't think that's going to work during the day. Here, during the day, it's saying that the ocean is warming up faster because the air is moving away from it. So these 2 don't work. Here, it's showing the interface again. That doesn't work because these are different substances. They have different specific heats. They're going to heat up differently, causing there to be a different flow than this. That's out. Here, we've got the beach, the sand, heats up faster due to its low specific heat. Rises up, needs to fill in with the cooler, more dense air that comes off the ocean, creating the sea breeze. So choice 4 is your answer. All right, the diagram below represents the circulation of air above Earth's surface at a coastal location during the day and at night. So day and night, we're dealing with sea breeze and land breeze. If you maybe flashcarded those things or you went back into your notes. So the diagram here is daytime, here is nighttime, land, water, same location. But notice that the arrows are going in a different direction. So the local air movement is best described as an example of 1, conduction between Earth's surface and the atmosphere above it. It's not conduction, we're dealing with fluids that are being heated up above. So no, that doesn't work. 2, condensation of water vapor during the day and evaporation of water during the night. Those things may be happening, but these arrows are not specifically for that purpose. So that's out. Convection resulting from temperature and pressure differences above land and water. That one looks pretty good. 4, greater radiation from the warmer ocean during the day and from warmer land at night. We're not dealing with radiation in that sense. Mostly when radiation is being spoken about, we're talking about the sun. And it won't be warmer land at night anyways. Warmer land does not work. So our answer is choice 3. So again, I hope you enjoyed this video. I hope if today is a rainy day, I brought a smile to your face. I know this has been tough on all of us. Let's keep it in high gear if we can. Give your independent practice a shot. Use your access points. Message me under the video if you need to, or in Google Classroom or in Jupyter, and we'll keep at it. Bye.